Solving a linear programming problem has many steps. In this video, I'll take each step and apply it in the context of a problem. The steps are laid out in the yellow box. They're also repeated in the context of the problem posed. I'll be using two pieces of technology to be able to solve this problem. Desmos.com is one that I use the most, and also matrixcalc.org. The problem posed is an electronics company has factories in Cleveland and Toledo that manufacture Blu-ray and DVD players. Each day, the Cleveland factory produces 500 Blu-ray and 300 DVD players at a cost of $18,000. Each day, the Toledo factory produces 300 of each type of player at a cost of $15,000. An order is received for 25,000 Blu-ray and 21,000 DVD players. For how many days should each factory operate to fill the order at the least cost? So in this situation, we assume that all the variables are related to one another in a linear format. What we need to begin with is step 1. Translate the problem into mathematical language. I usually take this first step, A, and organize the data into a tabular format. Everyone has their own way of setting up their tabular formats. In this problem, I chose to put Blu-ray, DVD, and cost. And across the top, Cleveland, Toledo, and the order requirements. So we know Cleveland can manufacture 500 Blu-ray and 300 DVD for a cost of $18,000 a day, while Toledo in a day can manufacture 300 Blu-ray, 300 DVD for a cost of $15,000. The order requirement is that we must have at least 25,000 Blu-ray. So that's a greater than or equal because it's at least. Also, the DVD needs to be at least 21,000. If we go under 21,000, we're not meeting the requirement of the order. Okay, it's important to identify what your variables are. I'm going to let X be the days of manufacturing at Cleveland. So Cleveland has variable X associated with it. And Y is the number of days of manufacturing at Toledo. And the goal is to figure out how many days I should manufacture at Cleveland, how many days I should manufacture at Toledo altogether to meet the order requirements for the least cost. So based on part A and B, I write my linear inequalities. 500 Blu-ray a day times the number of days at Cleveland plus 300 Blu-rays per day times Y, the number of days at Toledo, has to be greater than or equal to 25,000. Similarly, 300X is for DVD, and 300Y is also for DVD, but this time at Toledo, and we need at least 21,000. We have the other variable restrictions that X must be positive, so X is greater than or equal to 0, and Y is greater than or equal to 0. We can't have negative days of operation at Cleveland or negative days of operation at Toledo. Now the objective function is what I'm trying to minimize. I'm trying to minimize cost. Cost is here in the last row of our table. It's $18,000 a day for Cleveland, and X was the number of days. So 18,000 per day times X, the number of days at Cleveland, plus $15,000 per day times Y, the number of days at Toledo. We have our system of linear inequalities and the objective function. Now to turn to graphing. Step 2. Find the feasible set by graphing each inequality. You can graph these by hand or with technology. This particular image was created with Desmos.com. To do this feasible set, what I did is I graphed a straight line according to each inequality. First inequality was 500x plus 300y is greater than or equal to 2500. Now this is in orange, and over on right with a graph. That graph is in orange. We can see that the x-intercept is 50 down below, and the y-intercept was 83.333. This is also to be interpreted, that 0.3 repeating, as the fraction 1/3. Common decimals such as 0.3 repeating is supposed to be assumed that you know it's the fraction 1/3. I shaded to the left to show the area where the ordered pairs are not true. The second inequality is in purple. 3x plus 3y is greater than or equal to 21,000. The x-intercept was 70, and the y-intercept is also 70. There's my purple line. I shaded to the left to show the region where the solutions are not. The third inequality is x is greater than or equal to 0. This is a vertical line, and I shaded to the left. Y is greater than or equal to 0 is a horizontal line, and I shaded below the line. And remember, with all that shading, I was shading the areas where the solution is not. That means my feasible region, or feasible set, is the white area. All the ordered pairs in the white area are solutions to the system of linear inequalities. But for our problem, we are trying to find the one ordered pair that gives us the least cost while meeting the order requirements. With Desmos.com, this is pretty simple. What we need to do is find the points of intersection, or the vertices of the feasible set. So in our feasible set, far over here on the left, I can see a vertice of that occurs at the ordered pair 0, 83, and 1/3. I find that by double-clicking in Desmos, and it labels it for me. If it doesn't provide that in your technology, then look back at your work. Back here at our work, when I found the y-intercept for the first linear inequality, I came up with the ordered pair 0, 83, and 1/3. So I have my first vertice. I follow that orange line down and I find the next vertice. This vertice is labeled 2050 with the help of Desmos. If you don't have technology, what you need to do is recognize what two equations or inequalities form that point of intersection. We can see that the orange line and the purple line form the point of intersection. So down in step 3, I found that point B, by taking the two equations, 500x plus 300y equals 25,000, and 300x plus 300y equals 21,000, which are the equations for the orange and purple line, put them into a matrix and reduced it with the Gauss-Jordan method. I did this with matrixcalc.org. This reduced matrix tells me that x is 20 and y is 50 at that point of intersection. And we can see that Desmos verified that point of intersection is at 2050. Desmos is great for whole numbers and for decimal answers that have common decimal equivalencies, such as 0.33 being 1/3. But when you encounter a decimal that cannot easily be translated to a fraction, you're going to need matrixcalc.org or some other form of technology to find that exact point of intersection. And the third point or vertex for my feasible region is down on the x-axis at the ordered pair 70, 0. And that is found by looking back at our work with the purple line, and we see that the x-intercept was 70, 0. So I have point A, which is either 0, 83.33, or 0, 83 and 1/3, which I'll use the 1/3 to be accurate. Point B, which is 2050, and point C, which is 70, 0. Now that I have all 3 points, I need to evaluate which of those 3 points actually provides the least cost, or is the optimal point. Step 4, evaluate the objective function at each vertex. So we remind ourselves that the objective function that I was trying to find is the one for least cost. $18,000 per day for Cleveland and $15,000 per day for Toledo. I put all 3 of my vertices in the left side of this table just for organizational purposes. You don't have to use this table. You can do it by hand on the side or with a calculator. One at a time, take the x value of each ordered pair and the y value of each ordered pair. substitute it into the equation that needs to be optimized, and in this case we're looking for a minimization. Solve it and find that answer. So I did that for all three ordered pairs, and I found that the least cost occurs right here at $1,110,000. The interpretation is the lowest cost is $1,110,000 with 20 operating days, 20 because that is the X value of my ordered pair at Cleveland, and 50 operating days at Toledo, as that is the Y value of my ordered pair.